Hello everybody and welcome back to Differential Equations, and today we will be doing the exact differential equation. It is awesome. Okay, so before we do this, it does use partial derivatives. I'm not sure if you guys have taken multivariable calculus, but don't worry because I'll teach you the partial derivative. It is incredibly simple. Now, the first thing first is that the partial derivative operator looks like this. It isn't d dx, it's del x. If you're taking the derivative with respect to x, in this case it's called the partial with respect to x. It's pronounced del. So let's say you have some function z, and you want to derive the function z with respect to x. And of course z is a multivariable function. Del z del x. All other variables that are not x are treated as constants. You can also have del z del y or any other variable, and it's sometimes you'll have your function with multiple variables. It's denoted in this notation. Okay, and that is a big thing, right? There's all sorts of notation which you guys need to know. Del f del x, it could also look like f sub x. The second derivative of f with respect to x, or the partial rather, it's going to look like this. Maybe you can do some combination of the two. Doesn't particularly matter, but just understand that this is the notation that will be used, so you do not get confused. Alright, now let's do some partial derivative practice. This is not that difficult, excuse me. This first one, we will be deriving this function with respect to x. This first one looks like. And then the second one we'll have to take partial with respect to x, then partial with respect to y. But first we will do this one, and I will show you the answer immediately. It is very simple. So, power rule, 18x squared. Y to the fifth is a constant. This is a constant, dies. Kill the x, plus 8. Rock out. Okay, now try that with this. So basically just take... it's asking for partial with respect to x and then partial with respect to y. I already did the partial with respect to x, so you can just take the partial with respect to y. It's not that challenging. Pause. 3, 2, 1. Boom. Rock out. Okay, very good. That's basically, you guys should have it by now, but we can do some more. It looks a little complicated, but don't worry. Pause now, and I will reveal the answers to you. 3, 2, 1. Okay, very good. Cosine of y, constant. Ln of 14y, constant. Because we're taking it with respect to x. Rock out. Boom. Very self-explanatory, because you guys have taken derivatives an infinite amount of times. Really, there isn't much to explain. So it's just good at least you do some practice, and that's all you really need to know. Now, integrating a function of multiple variables. So you've probably caught on by now. It's the same exact thing in the sense that if you're taking the integral with respect to one variable, all other variables will be treated as a constant. So this is an example. We'll integrate y with respect to x. That is equal to xy plus c. Or perhaps this looks like chain rule, but guess what? Absolutely not. It's negative cosine of y times cosine x, as cosine x is indeed a constant, plus constant of integration. This is another example here. If you want, you could block out this answer and you can just do it yourself. First things first, this is called the total differential. This form here. Now, you will see the differential equation in some function of x and y times dx plus some function of x and y times dy is equal to 0. All you have to know is that to be exact, the partial of y, you can think opposites because this is being multiplied by dx. The partial of y of this multiplied by dx must be equal, identical. It must be the exact same as the partial of x of this bit multiplied by dy. And it's kind of easy to remember because it's kind of like opposite and weird. So let that sink in. And then of course I will show you some examples, and this will all be very easy. So this is an example. The following equation is exact. You have to test to see if it is exact. And we do that by partial with respect to y of this part partial with respect to x of this part. And we see that they are actually the exact same. So this one is an exact equation. And if they are not exact, I will explain what to do later, and it does involve an integrating factor. Okay, so if equation is exact, then the solution can be given by the following. So this is pretty interesting, actually. What we'll be doing is we'll be integrating m of xy dx with respect to x. So when you integrate it, it's all, you're not doing the opposite stuff. Like with the partial, it's partial of, with respect to y of that bit multiplied by dx. It's kind of like taking the derivative with respect to y of this stuff multiplied by the stuff with respect to x. It's kind of confusing. This is the opposite. It's very clean cut. We'll be integrating with respect to x on this side, and then we'll be integrating with respect to y on this side, and we'll be adding them. And that's equal to c, obviously. But as you can see here, something's kind of weird. We have a 0 in this, but as you can see, something's a little interesting here. If we look at the integrand of this second integral, we see that this function multiplied by dy, we're substituting the x for a 0. And this is actually equivalent to if we were to do the same with this bit, but instead of the x is a 0, it's a y is a 0. The reason why we do that guarantees we're properly integrating a simple closed curve. It's got to do with planes and stuff. If this isn't really much of a theory course, obviously I'm just teaching you how to solve these, but think about a plane if you've taken multivariable calculus. So let's just say we'd like to solve this. So we've already determined that this equation is exact. Very good. We've done the test for exactness, is actually what it's called. Then we just prepare our integrals here. Boom, boom, from 0 to x, boom, 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 plus 0 to y. If we look at our original function, sine of 0 is 0. This dies. So the only thing in our integrand is y cubed. And quite simply, we just evaluate the integral. And it's awesome. These exact problems are a lot of fun. And so very important that you remember to check for exactness, then integrate each part to respective variables and do it properly. So I would recommend, this page is basically just the recap, and it's all you truly need to know. And we have some practice problems, guys. I mean, I gave you the ammunition, you just gotta pull the trigger, guys. Write these down and rock out. I'd suggest you pause. I even have the formulas down here. Feel free to use the formulas, as that's what they're for. Give it a few seconds. Should have paused by now and solved them. Very good. I hope you guys did well. In fact, I actually knew you did perfect. Wait, what did you say? You got a perfect score? Very good. And if you didn't get a perfect score, actually, don't feel bad. Do it again. And even if you did them correctly, do them again and again and again. Okay, and now I'll actually provide to you the solution steps for equation number 2. Very good. So, first we check for exactness. Then we find out that it is exact. Then we just integrate, simply and respectively to each variable. Awesome, wonderful. Very good. Evaluate the integrals. Evaluate the bounds. And that's it. And we can simplify that up, and dude, it's flippin' awesome. There are actually a few ways to solve these partial differential equations when it comes to integrating. People have their own ways of doing it, but